Hello everybody, it's Tarun. Welcome to your 22nd tutorial in the Signal System and Control course. In this tutorial, I'll start with ROC property 6. Okay, so now let's get started. Okay, this property states that if x of t is two-sided signal, which means that if the line R of S is equal to sigma naught is in ROC, then ROC will consist of a strip in the S plane, which includes the line RS is equal to sigma naught. Okay, so what it is actually a combination of right-sided and left-sided signal. Okay, and if x of t is summation of the right-sided signal XRT and left-sided signal XLT, then its Laplace transform will also be like this, and its final ROC will be the intersection of ROC of right side and ROC of left side. Okay, so as in the example 3 I told you, which was the example of this property. Okay, in that example the first part, which was a right sided signal, and the second part was a left sided signal, and their intersection, which was there in that case, was the two-sided signal. Okay, so ROC property 7, for rational Fourier Laplace transform x of s, ROC is bounded by poles or extends to infinity. In addition, no poles of x of s are contained in the ROC. It means to say that either the ROC goes to infinity, or the last point in the ROC is a pole, okay, which is not included in the ROC. Okay, ROC property 8, for rational R of x of s, if x of t is right-handed, then ROC is the region in the S plane to the right of the rightmost pole. Okay, so now let's consider x of t as a right-handed signal. Okay, here in this case the rightmost pole is -2. Okay, and if the rightmost pole is -2, then its ROC is the region in the S plane to the right of this -2 point. Okay, which will be if this region. Okay, and if x of t is left-handed, then ROC is the region in the S plane to the left of the leftmost pole. Okay, so if it is left-handed, then the leftmost pole is this -4, and this will be the region in the ROC. Okay, and ROC property 9 states that ROC must be a connected region. Now let's see the next topic, which is inverse Laplace transform. Okay, we are having a Laplace transform x of s, which is x of sigma plus j omega, or the Fourier transform of x of t into e to the power minus sigma t. Okay, and x of t e to the power minus sigma t will be Fourier inverse of x of sigma plus j omega, which will be 1 upon 2 pi integration minus infinity to infinity x of sigma plus j omega e to the power j omega t omega, which I have written with the help of inverse Fourier transform formula for continuous time case. So now I have multiplied e to the power sigma t both sides, or I have taken e to the power minus sigma t to the right hand side. Then this function or expression will look like this. Okay, and now I have replaced sigma plus j omega with s, and by replacing sigma plus j omega with s, the limit also changes. Okay, so to solve the questions for inverse Laplace transform, we use the partial fractions method. Okay, in that partial fraction method, the Laplace transform is in the particular described expression. Okay, which is this expression, and after inversing your Laplace transform, the signal will be like this. Okay, which is summation of one or more signals. So if ROC is R of s greater than minus of ai, then x of I will be e to the power minus ai t ut, and if it is less than minus ai, then it will x of I will be minus e to the power minus ai t u of minus t. So I'll suggest that you remember these 2 points because they'll help you in solving the questions very quickly while you'll be solving them. Okay. So now let's see one example. Here I am having x of s as 1 upon s plus 1 into 1 s plus 2. I can rewrite it in this manner as 1 upon s plus 1 minus 1 upon s plus 2. Okay. So there are 3 possibilities for ROC. Okay. First one is ROC is greater than minus 1. This will happen when the first ROC for first part, which is 1 upon s plus 1, will be greater than minus 1, and ROC2 for 1 upon s plus 2 will be R of s greater than minus 2. Then your whole ROC will be R of s greater than minus 1. In that case, your x1 of t will be e to the power minus t ut, and x2 of t will be e to the power minus 2t ut. The second case is when R of s is less than minus 2. In that case, the ROC of first part of the expression will be less than minus 1, and the ROC for the second part will be less than minus 2. Hence, giving us the new ROC or the final ROC as less than minus 2. In that case, your signal x of 1 and x2 of t will be minus e to the power minus t u of minus t and minus e to the power minus 2t u of minus t respectively. And the third case is when R of s lies between minus 2 and minus 1. In that case, the ROC of first part will be less than minus 1, and for second part it will be greater than minus 2. And in that case, your x1 of t will be minus e to the power minus t u of minus t, and your x2 of t will be e to the power minus 2t u of t. Okay. Moving forward, now let's see some low pass filters. Okay. The first one is the first order systems. Okay. And for the first order system, your differential equations look like this: tau dy over dt plus yt equals to xt. Okay. And I can find out the Laplace transform for this function. Okay, and your equation will look like this. Or let's first see the properties of the Laplace transform first, and then I will take you to these low pass filters because first when you understood the properties of Laplace transform, then it will be easy for you to understand these low pass filters. Okay. So now let's see the properties of Laplace transform first. If x of t is our signal and x of s is its Laplace transform and its ROC is R, then according to the linearity property, if our signal A is ax1 plus ax2 or ax1 plus bx2, then the Laplace transform will be a capital X1 plus b capital X2. Okay, and its ROC will intersection of ROC1 and ROC2. Next property is time shifting property. If the ROC of x of t we all know is x of s, what will be the ROC of x of t minus t naught? It will be e to the power minus s t naught capital X of s. In this case, ROC will remain unchanged. Okay. The next property is shifting in s domain, which means that I am having the Laplace transform as x of s minus n naught. So when will this type of situation happen? When we multiply our input signal x of t with e to the power s naught t. Okay, then the Laplace transform gets shifted in the frequency domain or in the s domain, and here in this case ROC will be r plus r of s naught. Next property is time scaling. If I multiply independent variable t with a scalar a, then the change in the Laplace transform will be 1 upon mod a x of s upon a. In this case, your ROC gets reduced by the value a, okay, or it will be r divided by a. The next property is conjugation property. If I take the conjugate of input signal x of t, okay, then the Laplace transform change will be the Laplace transform will be conjugated, but the variable s will also be conjugated inside, which means that x conjugation, s conjugation, and in this case ROC will remain unaltered. The next property is convolution property. If I am taking x1 of t convolution x2 of t and finding out their Laplace transform, then the Laplace transform will be x1 of s into x2 of s, okay, and their ROC will contain intersection of both. So this is one example where x1 of s is s of s plus 1 upon s plus 2 and x2 of s is s plus 2 upon s plus 1. So the next property is differentiation in time domain. If I differentiate my signal in the time domain, then I'll get the Laplace transform multiplied with s outside, okay, and its ROC will contain r only. And for differentiation in s domain, if I multiply my input signal with minus t, then the Laplace transform will be differentiated in the s domain, and its ROC will be equals to r only. Okay, the next property is integration in time domain, or you can just compare it with the integration property in the Fourier transform only. For integration minus infinity to t x of tau d tau will have the Laplace transform x of s upon s, okay, and its ROC will contain r intersection r of s greater than 0, okay. So now let's move back to the low pass filters, okay. So now before starting the low pass filters, I'll suggest that you practice some examples from the book on the Laplace transform and the inverse Laplace transform. So you solve the examples. I'll see you in the next tutorial. So thank you guys for watching.